Hello everyone, my name is Leah Weber and I'm a graduate student at the University of Illinois at Urbana-Champaign. And today I'll be presenting our paper, Phyolin, Identifying a Linear Perfect Phylogeny in Single-Cell DNA Sequencing Data of Tumors. And this is joint work with my advisor, Mohammed El-Kabir. So as many of you are aware, tumors arise as the result of an evolutionary process. And this process begins with a single founder cell that gains a somatic mutation. Then over time, these cells may gain additional mutations. And if these mutations are advantageous to the cell, it'll give rise to a clonal expansion or growth of the tumor. And the end result of this process is a heterogeneous tumor made up of a mixture of clones with distinct genotypes. And consequently, one of the key reasons why cancer is such a challenging and complex disease is because of the heterogeneous nature of tumors. So one way to model this process and gain insight into the degree of heterogeneity is with a phylogeny, where the root of the phylogeny represents a normal cell and the leaves of the tree represent the extant cells of the tumor. And these phylogenies can be used in many important downstream analyses. For example, it can aid in treatment decision-making, such as identifying specific clones to target. We can better understand how cancer spreads and metastasizes. And we can begin to identify evolutionary patterns across and within groups of patients. And this will help us to better understand and study the mechanisms that are driving these processes. So comparing evolutionary patterns also includes looking at modes of evolution. So a mode of evolution is a generalized description of the process of how cells respond to selected pressures and evolve. And in a review paper by Davis, Gao, and Navin, they summarize the existence of 4 modes of evolution. And 2 of these major categories are linear and branched evolution. So in linear evolution, this results when subsequent driver mutations develop a strong selective advantage and outcompete other clones during a clonal expansion. In branched evolution, the clonal lineages may diverge from a common ancestor, resulting in a tree-like pattern of evolution where the subclones evolve in parallel. And both branched and linear modes of evolution have been seen in cancers like ovarian, renal cell carcinomas, and leukemia. So one important reason why we might want to distinguish between a mode of linear and branched evolution is that branched evolution results in increased intertumor heterogeneity or a greater diversity of the subclones. And consequently, increased diversity is more difficult to treat because there exists a wider range of responses and adaptations to the selective pressures that are applied during cancer treatment, such as chemotherapy. So this often results in poor treatment outcomes and lower survival rates. So this has motivated the main question of our work, and that is, if we are given single-cell DNA sequencing data of tumors, can we discern between linear and branched evolution? So I'll just pause here and give a quick outline of the remainder of my talk. So first, I'll give a formal statement of the problem and discuss its complexity and our methods. Then I'll give some results of our simulation study and an application to real data. And finally, I'll summarize our conclusions and discuss some of our future directions. So one way we might go about answering our question is to try and reconstruct the evolutionary history of a tumor given sequencing data. And one very exciting advancement in cancer research has been the rapid development of methods for single-cell DNA sequencing of tumors. And the advantage of these methods is that it provides unprecedented resolution of the clones of the tumor because we can observe the co-occurrence patterns of mutations within a single cell. So for example, here we can observe that the green, blue, and red mutation all co-occur together in a single cell. And there's a number of different single-cell methods, and this work will be utilizing single-cell methods that identify point mutations. So here you can see we have each cell and we have our mutations, and then there's a 1 if that mutation is present in that cell. And although there are a number of exciting advancements in single-cell sequencing, there's also a few drawbacks as well. So for some methods it can be expensive and it can be an intensive process resulting in low throughput. But one of the biggest drawbacks is that it's highly prone to errors in the sequencing process. And these include false negatives, false positives, missing data, and doublets. And a doublet is where two cells are simultaneously sequenced as if they were one cell. And of these error types, the most problematic are false negatives, and these can have error rates as high as 40%. So to reconstruct the evolutionary history of a tumor, in addition to data, you'll also need a model of evolution. And there are many models for cancer evolution ranging in their complexity and assumptions. But one of the most common models is the infinite sites model, which states that once a mutation is gained, it can only be gained once and never subsequently lost. So with the infinite sites assumption, an evolutionary history can be modeled as a two-state perfect phylogeny, where the root is all zeros and represents a normal cell, and this is because the equivalent binary matrix satisfies the 3-gamete condition. And currently there exist a number of methods that combine error-prone single-cell data and a model of tumor evolution to reconstruct the evolutionary history. For example, under the infinite sites assumption, we have site and OncoNem. However, these are challenging inference problems, and the methods can be sometimes slow in practice and result in non-unique solutions. And this challenge is further complicated because typically only a single biopsy is available, because the process of obtaining longitudinal biopsies can be a painful process for a patient. So for these reasons, we decided to take a step back and try to ask an easier question. So this brings us back to our original question. If we're given single-cell data, can we just discern between the mode of evolution being linear or branched? And this was a question that was recently raised in a paper by Azer and others, where they utilized deep learning to classify the topology as linear or branched. And we wanted to see if we can develop a combinatorial approach to answer this question. So to achieve this, we first formulated a hypothesis test where the null hypothesis is that the single-cell data represents linear evolution, and the alternative hypothesis is that the mode of evolution is not linear and therefore contains branching. And I'll just note here, in our work, we narrow our scope to focus only on false negative errors because they're the most prevalent of the single-cell error types. So in order to perform this hypothesis test, we require a method to calculate an appropriate test statistic. So to facilitate this, we formulated the linear perfect phylogeny flipping problem. And the input to our matrix is a binary n by m matrix, where n is the number of single cells and m is the number of mutations. And the output is the minimum number of flips from 0 to 1, such that matrix B will represent a linear perfect phylogeny. So here a flip is always from 0 to 1 because we are focusing only on the possibility that an entry may be a false negative. So by looking for the minimum number of flips, we are looking for the minimum entries in B that must be corrected under our null hypothesis that the single-cell data matrix B represents linear evolution. So to solve this problem, we require a way to categorize a binary matrix B as equivalently representing a linear perfect phylogeny. And visually, we can recognize that the mutations in the binary matrix can be reordered in a way where we can observe this kind of staircase pattern or phenomenon in matrix B. And so we can slightly formalize this concept. So we introduce a set called the one state of a mutation, which contains all the cells that harbor that mutation. So for example, the one state of the red mutation in this example would include cells 2 through 5. Then we could say that B represents a linear perfect phylogeny if there exists a total order of the mutation 1 states. And this basically allows us to formalize this staircase property of linear perfect phylogenies. So once we get a solution to the linear perfect phylogeny flipping problem, then we can use our output to perform a hypothesis test. So recall that our null hypothesis is that our single-cell data represents linear evolution. So using the outputted number of flips in the corrected matrix B prime, then we can estimate the implied false negative rate beta hat. And just recall we have two assumptions here. The first is that the model of evolution is the infinite sites model. And we also have an additional assumption that we can obtain an estimate of the system false negative rate for the sequencing technology that's being used. And there are methods to obtain these in practice. And so finally we can check if our implied false negative rate beta hat is greater than our system estimated false negative rate. If that's true, then we can reject the null hypothesis that single-cell data represents linear evolution in favor of branched evolution. So in our paper, we showed the linear perfect phylogeny flipping problem is NP hard by reduction from a known NP complete problem, the chain graph insertion problem. So if we're given a bipartite graph G with vertex sets x and y, we can define the neighborhood of each vertex in y as a set of vertices in x that are adjacent to that vertex. So for example, the neighborhood of A is going to be the set containing vertices 1 and 2 in x. Then a bipartite graph G is a chain graph if there exists a total order of the neighborhoods of y. So the chain graph insertion problem asks if k edges are added to a bipartite graph G, is the graph now a chain graph? For example, if k equals 3, then we can add the following edges to G such that our graph will now be a chain graph. And we can reduce the chain graph insertion problem onto the decision version of the linear perfect phylogeny flipping problem, which asks, does B represent a linear perfect phylogeny when k bits are flipped from 0 to 1? So we simply map the vertex set of x onto the rows of matrix B, and then we map the vertices of y onto the columns of matrix B. And then we can map the edges as a 1 in our matrix and 0 if an edge does not exist. And this can be done in polynomial time. So we can see by the equivalence of the neighborhood condition and the 1 states for representing a linear perfect phylogeny, then we have the lemma that a bipartite graph G with k edges inserted is a chain graph if and only if B represents a linear perfect phylogeny when k bits are flipped. So to solve the linear perfect phylogeny flipping problem, we developed a method named Phyolin using constraint programming to help us calculate the test statistic. And our objective here is to find the minimum number of bit flips so that the output matrix B prime represents a linear perfect phylogeny. So to do this, we have two sets of decision variables, the set x with domain 0, 1, where each variable is going to represent a bit in our output matrix B prime, which has the same dimensions as our input matrix. And then we have a set of variables C, which identifies the position of the mutation in the total order. And this is a helper variable for our model constraints. So overall, Phyolin has 3 constraints. The first constraint prevents flipping of bits from 1 to 0, or basically preventing false positives from occurring. As in this version, we're only considering false negatives. And the second and third constraint ensures that our output matrix B represents linear perfect phylogeny. So we need to basically find the total order with a global all different constraint on our C variables, and then ensure that the 1 state for every pair of mutations is a total order. To evaluate Phyolin, we utilize a simulation study as well as real data. So we model our simulation study off of a recent acute myeloid leukemia cohort where microfluidic targeted sequencing was used to reconstruct the evolutionary history of 77 patients using CITE. And the evolutionary histories of these patients included a mix of branched and linear modes of evolution. And we randomly selected 6 patients with linear evolution and 6 patients with branch evolution, and utilized the inferred trees to simulate single-cell data for our simulation study. We used a false negative rate of 0.05 because this was the false negative rate that was estimated for the technology in the original study. So the number of mutations per patient ranged from 3 to 7, and the number of cells ranged from about 4,600 to 9,300. And we simulated 10 single-cell data sets per patient and utilized IBM iLog CP Optimizer to solve each instance with a 500-second time limit. So here are the results on the simulated data set. So this graph here shows each simulated patient in the study on the x-axis, broken into 2 groups if they have a ground truth linear mode of evolution or branched evolution. And the y-axis is the mean estimated implied false negative rate, averaged over the 10 replications with the error bars shown. And so as you can see, for every patient where the simulated mode of evolution was linear, the mean estimated false negative rate was less than the simulated system false negative rate beta star of 0.05. So in those cases, we did not reject the null hypothesis that the mode of evolution was linear. In cases where the ground truth mode of evolution was branched, we correctly rejected the null hypothesis in favor of branched evolution. And we also compared Phyolin against the deep learning approach that I mentioned earlier. So to do this, we had to retrain the neural network to facilitate an input size of 9,300 cells by 7 mutations to accumulate our simulated data. And we used padding for any of the instances that were smaller. Other than retraining on the input size, we utilized all other default hyperparameters. And I just want to point out, they formulate the problem as a classification problem. So their neural network outputs the probability that the topology is linear. And so we use a cutoff of 0.5 for classifying a new instance as having a linear topology. So as you can see, for the linear patients, it only correctly classified 2 out of the 6 patients. And for patients having a branched evolution, it correctly classified 4 out of the 6 as having branched evolution. So with Phyolin, we found that inputs with a simulated ground truth of linear evolution finished faster with a median runtime of under 1 minute, with all but one simulated instance completing in the time limit. And the branch instances took a median time of 150 seconds, and 25 of the instances used the entire 500-second time limit. And we compared this against the runtime for the deep learning method, where one of the advantages for deep learning is that once a network is trained, classifying a new instance is very fast. However, as in our case, it often requires training a network to accommodate the appropriate input size. So we used 5,000 random training examples that were generated as part of their method, and a total training of 500 epochs. So after 36 minutes, the training accuracy was around 64%. And after the total training time, which took a little over an hour, there was just minimal improvement in the accuracy on the training set. We also applied Phyolin to 2 patients with acute lymphoblastic leukemia, as well as compare the results against a deep learning approach. Against the deep learning approach. So in this data, the input size was much smaller in terms of the number of cells, and the number of mutations was slightly larger at 16 and 10 mutations per patient. We used the system estimate of the false negative rate from a paper by Kuipers in 2017, and the estimate was 0.18 for beta star. So in the case of patient 2, Phyolin strongly rejected the null model of a linear mode of evolution, which agreed with the deep learning approach in this case, as well as a number of other published phylogenies for patient 2 that contain branching. So in the case of patient 6, Phyolin failed to reject the null model of linear evolution and is again in agreement with the classification of the deep learning method. However, we did note that in the study by Kuipers, they estimated with high probability that patient 6 actually had a mutation loss. So this actually technically results in a branched evolution. So this result leads to some interesting directions for future research, because we might want to consider a spectrum of the degree of branching. Since a tree with a loss is technically branched here, but the tumor heterogeneity would be less than for a tree with a greater degree of branching. And we can also see that there's value in extending Phyolin to other models of tumor evolution, such as ones that allow mutation losses. So in conclusion, we found that Phyolin is a fast and easy to use and accurate method in assessing the plausibility of linear evolution. And in practice, this provides a means to assess the degree of intertumor heterogeneity without relying on more intensive phylogeny inference methods. Our code is currently available at the provided link. In terms of future work, we are very interested in incorporating other sequencing errors such as doublets and false positives. And we would like to extend to other types of single-cell sequencing technology, such as data used to infer the evolutionary history of copy number aberrations. As previously mentioned, we are also interested in exploring models beyond the infinite sites model. And finally, in the case where an experiment design may be biased, such as insufficient power to detect rare subclones, our hypothesis test may be sensitive to type 1 errors. So future work will also look at incorporating ways to control for the type 1 error caused by biased sampling of cells. So thank you very much for your time and attention, and I would also like to thank and acknowledge the members of my lab and my classmates who provided very helpful feedback on this work. Thank you very much.